Okay.
All right, so let's see. So yeah, so I'm going to try to follow up to stuff that I was talking about last time. So yeah, let me just try to remind us of what I was talking about last time. So I was talking about this idea of a composite of covering projections and how the Galois group of the first stage acts on the Galois group of the second stage. They fit together to form a short exact sequence, which we can interpret as something like the Galois group of the first stage acting on the Galois group of the second stage, and this phenomenon. The point of thinking about this phenomenon is that it's really showing up in Grothendieck-Teichmüller theory, and so we have. Let's see. I guess I had the first stage and the second stage. I guess it depends on how you count, from which direction you're counting first and stage. I guess I'm thinking of going from the base space as where we're starting from, and then we're going to progressively more refined covering projections, covering spaces, and so this is showing up in Grothendieck-Teichmüller theory, and the way it's showing up in Grothendieck-Teichmüller theory is that the first stage is really the arithmetic stage, and the second stage is a geometric stage, so that we get an arithmetic Galois group, like the absolute Galois group of the rationals, acting on these geometric Galois groups. And
I have a slogan which I didn't have the nerve to say to you last time, but I'll say it now, which is
sorry, go ahead.
You were like wondering why they come in that order, and I think you know perfectly well why they do, but my slogan was something like, you need new numbers to draw new curves or something like that. Draw new figures. So like first give yourself new numbers.
I'll have to think about that.
Do stuff with them. You do geometry with them. Anyway, it's an interesting thing to think about.
Yeah, something like that is true. I'll have to think about it. So I want to try to follow up on that, and in particular, so in the past, I've worked out some examples of designs. Well, these Gaussian designs that I've talked about, we worked out some examples in some detail. And I want to try to apply those ideas to these examples. And so you might remember that the examples of designs for which I was able to work with them most explicitly and concretely were the genus 0 designs. And I always had vague plans to generalize beyond that, but I was having enough fun with the genus 0 case that I didn't get to really going beyond the genus 0 case very much. But my vague plans for today do involve thinking about going beyond the genus 0 case, and it's sort of provoked by these ideas about the composite covering projections of Grothendieck-Teichmüller theory. So let me go ahead and try to get more specific about what I'm trying to say here.
Can I interject some irrelevant
Go ahead.
question? So I was wondering if you're talking about this short exact sequence. I was wondering if you ever figured out the answer to a question you raised last time, which is whether there's a non-trivial 2-co cycle in that type of sequence, just in general.
in general, there should be, but I don't think I've quite run into that yet in any of the examples. So I mean, I could be wrong, but I mean, there should be, lots of good, fun examples like that. But I haven't actually run into any yet. But it could be, I could be, maybe I really have run into them and just didn't notice them, or have been making a mistake or something like that. So, yeah, so let me try to remind us of some examples here. My favorite examples that I always use that are easy to calculate with. So there's my favorite example of a pair of designs that are in the same Grothendieck-Teichmüller orbit. And so what do they look like? Something like this. And like this. Did I get it right? I hope that's sort of correct. And sometimes I use a color scheme, 3 colors, green, red, and blue, to keep track of the 3 branch points of the covering projection. So I guess I often have these be green. Is that where the greens are? I guess. That's right. And the reds are right in the middle. That's right. That's supposed to be red. Which would be, there's one right there. And there's one right there. And there's one right there. And the blues. That's right. I hope this is somewhat correct. And let's see. So these are genus 1. But
yeah, for a while I was getting completely confused about how you were drawing these genus 1 things and then doing a bunch of genus 0 reasoning with them, even though you did explain it.
Yes.
So you take a further quotient of these to get the genus 0.
Yes, and you can think of it as modding out by 180-degree rotation around the center there. And so how does this work? So, well, right. So I like to keep track of the vertex census of the design. So in the genus 1 case, we have the 3 colors are green, red, and I guess I usually list them in the other order: green, blue, and red. Sorry. And in the genus 1 case, everything is just, all the greens are for, let's see, what am I trying to say? This is a very sloppily drawn Young diagram. And the reds, similarly, I mean, I guess those Young diagrams have what, 3 rows and 4 columns. The 3 rows correspond to the 3 red dots or to the 3 green dots. And the 4 the fact that each row is length 4 corresponds to the fact that, I guess there's various ways to think of it. Like each red is surrounded by 4 greens. Each green is surrounded by 4 reds. And then the blues. Is this right? That should be like, there's 6 blues. And I guess they're each surrounded by 2 reds or by 2 greens or something like that. But in the genus 0 picture, which you're modding out a lot, and you get, what is it? So you get a 4 and a 2. And for the greens, and the same for the reds. Whereas for the blues, you're getting 2, 2, 1, 1. And I guess, yeah. And yeah, so we'll work more directly with the genus 0, and we'll label the rows by letters A, B, C, D, E, F, and G, H. And I'm trying to remind myself of how this works, but without getting lost in too much of the details. Well, I'll start writing down some of the polynomials and stuff, and then we'll try to remember the conceptual interpretation of this. So let's see. I guess we're gonna have a rational function, a meromorphic function. It's like a map from one genus 0 thing to another genus 0 thing. So so it's going to have like a numerator, which is going to be associated to the green, and I guess maybe the blue, maybe that's the denominator. There are different conventions that I use sometimes. And the red, I guess that's associated to the one-erator. One-erator. So again, the idea is that a rational function has more than just numerator and denominator. The numerator is like telling you about the fiber over 0. The denominator is telling you about the fiber over infinity, but there are all those other fibers, including the fiber over 1.
The
one-erator. What?
You once said fiberator.
Fiber. I said that, or did you?
Yeah,
I did.
Yeah, then it cut.
Almost.
Yeah. Okay.
So,
yep, I remember.
Making use of these letters here, I want to say something like that. The numerator is going to go look like x minus a to the 4th times x minus b squared. And the denominator is going to look like x minus c squared times x minus d squared, x minus e, x minus a. And this might be, these letters, I might have this be a slight permutation of the letters that I used the previous time that I did this calculation, but it's okay. And then the one-erator would be what? X minus g to the 4th. X minus h squared, or something like that.
Yep.
And right, and the sort of one of the sort of magic things that makes this work, and there's a couple of magic things that make it work easily enough that I could do the calculations on Mathematica, but what am I trying to say? That the k-orators of a rational function lie on a straight line. They're sort of collinear. And in fact, right, and in fact, the way it sort of simplifies in this Gaussian case, the Gaussian case has this sort of duality between the Gaussian integers and the deep holes in the Gaussian integers. That's the duality between the green vertexes and the red vertexes, and the blue vertex is a kind of neutral in the red-green duality. So that actually ends up meaning that could
you remind me what you, sorry,
yes.
the association that you're now using between GBR and 0, 1 and infinity? I figured that out.
I'm constantly in danger of permuting that as
okay.
well.
Well, okay, but anyway, I should be able to, let me just say it then, because I mean, at least given what your current conventions.
Yes.
So G is connected to 0. Because
that's right. The numerator is 0.
Yeah.
Right.
The denominator is connected to infinity and R. So blue is infinity and R is 1.
That's right.
Yeah, okay.
That's right. And but yeah, I'm just constantly in danger of accidentally permuting that from one calculation to the next. So I'm hoping that won't get me in too much trouble. But yeah, so the idea is that right. In fact, for this calculation, maybe it makes more sense to, instead of having the denominator be infinity, maybe I should really make it 1/2 or something, so that it's literally at the midpoint of the numerator and the denominator. Maybe that would be a better convention to use in this case, because again, like I say, in the duality between the Gaussian integers and the deep holes in the Gaussian integers, the green vertexes and the red vertexes, the blue vertexes are completely neutral in that duality, so they live right in the midpoint. So in other words, it's like there's a set of there's a system of equations that's relevant here, and so the variables should be those 8 letters, A, B, C, D, E, F, G, H. And then the important constraint should be saying that the blue polynomial should be exactly midway between the green polynomial and the red polynomial. So, this is right. So this, you worked out how the coefficients of this polynomial should be exactly halfway between the coefficients of this polynomial and the coefficients of this polynomial. And that gives you a system of equations in these variables. And you solve that, and it basically, well, if you solve that, there's still a little bit too much flab in the system due to, the triple transitivity of the Riemann sphere. But if you could get rid of that flab by just randomly picking a few base points to get rid of the triple transitivity, then you end up with a zero-dimensional, for some magic reason, you end up with a zero-dimensional space of solutions to this equation, which means that this system of equations is succeeding. It succeeds in identifying exactly the Belyi projection that we're looking for, this meromorphic function from one Riemann sphere to another Riemann sphere that will be Meromorphic function, I guess, is it degree 6 or is it degree 12? I guess it's degree 6, I guess. Yeah, because of these 6th-degree polynomials. And so yeah, I'm trying to remind us of how this works, how we can calculate the specific, right. So what is this doing? This is getting us from a purely combinatorial description of the design to an actual meromorphic description of the design as, a specific meromorphic function. So going from one genus 0 curve to another genus 0 curve. And so how does this fit into the composite covering projection picture? So it goes, let's see if I can get this to work. So it should be something like the rational numbers adjoin K and adjoin the inverse of K to get rid of 0, and adjoin 1 over 1 minus K to get rid of 1. So now we've got a thrice punctured Riemann sphere here. And yeah, so that's our base space, or that's the algebraic thing corresponding to our base space. And then corresponding to our covering projection is this thing. I'm not sure I'm using the terminology exactly correctly, but I want to say that this is like an étale homomorphism of commutative rings. Let's hope that that's close to being correct. And so it's like, we want something like Q. And then we put in these extra variables. And then we put in, those extra constraints that I was describing. I'll just, the constraints that say that, that get this down to a 0-dimensional variety. And
are we thinking of these rings as fields? Are these rings fields?
No, they're not quite fields because it's just a polynomial ring. I mean, if you want to get a field, that's the voodoo limit where you remove all the certain needles into every point of the space.
But you are using Q as you're using the field. Sorry, this is probably a stupid question, but you're using the field Q, but you're not trying to make the arithmetic thing. You're not trying to use algebraic integers in everywhere.
Right. It might be fun to do that. Might be an interesting thing to do.
I was just getting confused because of this arithmetic geometric thing. So you're treating the geometry more carefully than the
yes, and not necessarily with any really great excuse, but I guess part of my reasoning is that for purposes of the geometry, we really do want to limit the ramification. We don't want to have branch points. So I've put punctures right where all the branch points are, so that
okay,
right. So there there may be something somewhat universal about the next thing that we're going to have, which is going to be something, well, actually, we're not doing the universal example, but there is the universal example, right? Where you completely unwrap the thing around the three punctures. And so it becomes like, you know,
Uh-huh.
I want to say it's like homotopy equivalent to that infinite television aerial thing or something like that, you know, for the
The free group on two generators.
yeah, the free group of on two generators when you take the you know what I'm talking about. It's
universal.
yeah, I mean you got this figure eight whose fundamental group is the free group on two generators, and then you can draw the universal cover of that figure eight, and so it looks like a very unwrapped figure eight, and it looks kind of like a television antenna or something like that, an infinite television antenna. I think somebody even calls it the infinite television.
Yeah, I guess young people won't know what that means, but yeah, I know.
Right, yeah, that's true. But it's very
yeah, I know what it looks like. I could draw it.
But right here we're doing not the universal thing. Here we're just doing a very non-universal covering space. And so what is this one going to look like? This one's going to look like and then one more variable, which I've been writing R as the next variable for R standing for root. You know, it's kind of like the root of this polynomial or something that we've been talking about. These polynomials have been, but maybe I should just call it X. So we wrote the polynomials as polynomials in X. And so we still have, you know, those same constraints on A, B, C, D, E, F, G, H that get us down to, let me sorry, I've got this infinite drawing tablet, and I still get the writing crowded together there. So it's, sorry, I went through our separated thing. So there's, you know, one more relator which says that X behaves as it should. How do we say that? I mean, there's all sorts of ways to say it, but is there some convenient way to say it that right? I mean, there's this. Well, I guess what I'm trying to say is this. I'm trying to say that R is a root of a polynomial. And where the polynomial P
is R the same as X?
Yes, I said before that I've been using R, and then I just write. Okay, so okay, let me say it. X. Where P is, you know, this polynomial that's obtained from, I guess it's obtained from the numerator and the one-orator. I'm not sure I'm doing this exactly right, but I want to say something like P is K times the numerator plus 1 minus K times the denominator. You know, so for example, when K is the numerator, sorry, when K is 0, I should be getting the numerator. And when K is 1, I should be getting the one-orator. Did I say that right? Okay, so I said denominator, but maybe I should have said one-orator. It's hard to read my writing anyway, but again, this is where I could get myself confused by getting my conventions permuted here. So right, I'm writing this out in a wordy way, but you're supposed to basically see how to write this as just, a presentation of a commutative ring.
So what is that? I'm trying to figure out a good way to say like what that is accomplishing.
Should I try to think it out loud, or do you want to?
Yeah, that'd be nice. Yeah, I could do it maybe, but you could do it.
Yeah, it's supposed to be saying that we're, getting this extra coordinate for the design, for this genus 0 design. So right, I mean, it's basically saying that over each point in the base space, we're getting 6 roots of this 6th degree polynomial. Right, we have this linear family of 6th degree polynomials. We have a linear family of 6th degree polynomials. Did I fail to emphasize that before? I mean, I said something about the midpoint, the denominator or the half-orator should be the midpoint of the numerator and the one-orator. But the emphasis is not just that it happens to be the midpoint, but that the whole family of these things is collinear, that there's a linear family, right? I mean, yeah, right. What am I trying to, what's the idea? The idea is this, there's this fact that I learned pretty recently, which maybe I should have learned a long time ago, or I don't know. But the idea that, a rational function thought of as this covering of the Riemann sphere by another Riemann sphere, that if you encode the fibers of that meromorphic covering, if you encode those as polynomials, then you're getting a collinear family, or a linear in some sense, a collinear family of polynomials.
How is the fiber?
What's that?
How is the fiber a polynomial again? It's the roots of the polynomial?
Yes.
Okay, yeah.
That's right. That's right. That's right. And again, there's a whole bunch of things I'm being sloppy about here. So like, I think it worked out. If you really want to think of it as, maybe I should say, instead of saying a linear family of polynomials, maybe we should say collinear or affine linear, because I think what you do is you normalize all of these polynomials to be monic, and then when they're all monic, they lie on an affine subspace, an affine one-dimensional subspace. So there's just little normalization issues to be dealt with here, and I'm trying not to worry about too much that stuff. I'm just trying to remind us of the general big picture, conceptual big picture of how this works.
So you started, so you drew this little short exact, this sequence of covers.
Yes. Yes, composable pair of covering projections, or composable pair of étale homomorphisms.
So that middle thing, thought of as a space, it's a it has, you think it has like 2 points over each. So the point at the space of the base is like the 3 punctured Riemann sphere, and then above that you get this other space, and you said you wanted the fibers of that second one up to be 0-dimensional varieties. So the points in those fibers, well, you're claiming from calculation that they're really just 2, namely these 2 different connected to these 2 different designs that you've got. Is that right?
I think so. I admit I'm a little bit I think you're right, but I mean, at some point here, in order to really bring out, let me think for a second. What am I trying to say?
So I guess
I'm getting a little bit worried. It's going to be okay, but I'm getting a little bit worried because it seems like I've got a single, composable pair here, but it somehow includes both designs in it, right?
Yeah, that's what's confusing me. So
Yeah.
like I thought, so like you could in principle like take that middle algebra and like put in some extra equation that would like pick out which of those two designs that you really want.
Yes, and in fact, what you maybe what you might want to do is you might want to take the that second étale homomorphism and perhaps tensor it with like maybe the complex numbers or something like that, and then after you tensor it with the complex numbers, pick out a particular solution, complex valued solution for the A, B, C, D, E, F, G, H, and then sort of like the fiber, not sure fiber is the right word, but the inverse image over that will be one of the designs, and then the inverse image over the other will be the other one of the designs, or something like that.
So were you wanting to work with both designs at once, or are you just sort of accidentally doing that? I can see why you might want to, because the Grothendieck-Teichmüller group's supposed to be like acting on the set of designs, so you might want to like have a bunch of them all sitting around.
Well, I think the answer is that I should have a definite. It'd be good if I had a definite decision about the answer to your question about which one I want. But I'm confused enough that I'm. In particular, one of the things I'm confused about here, and I'm confused, maybe I'll make it sound better. I'll make it sound like I'm being sloppy rather than that I'm being confused. Because I know I could get myself unconfused. So, I'm just being sloppy about it. But the thing I'm being sloppy about, one of the things I'm being sloppy about here is, and it's probably a very similar thing to what we were being sloppy about in the previous conversation, which is, there are conceptual and mental pictures here where you focus on the normal covering projections, the Galois covering projections, versus there are ones where you focus on just the unnormal ones. And I'm being very sloppy about which ones of those I'm dealing with here. It looks like, from what I'm writing down here, it looks like I'm writing down non-normal ones. I don't know, right? And another excuse I have for getting confused, and why it's a way of being sloppy again, is that, right, if we're I said something about tensoring with the complex numbers. Right. If you try to visualize this before you're tensioning with the complex numbers, then you're trying to visualize, some of these mysterious arithmetic dimensions. So of course you can't visualize. Of course I can't visualize it. But right, if you tensor with the complex numbers, then if you did things right, the whole discrete solution space is just it's a quadratic thing. So it's got two elements. So I think what's going to happen is the whole thing after you tensor with the complex numbers, because the thing is a quadratic number field, it's going to just split into two separate pieces, and that's going to be the two separate designs. I think that's what's going on, but I admit I'm being very sloppy about that. I'm being very sloppy about that, and I'm being very sloppy about the issue of the normal subgroups versus, the normal.
So when you're doing the normal covering, is that the one where you need to include both designs? Because you're not.
I think that's
you're
right.
Not making up your mind in an arbitrary way, and so normal subgroups are sort of like subgroups where you haven't made any.
Is that the same? Is that the
arbitrary decisions?
The same contrast? I'm not even sure that is the same contrast, but again, I feel like I can get myself unconfused about this when necessary, but I'm not sure it's necessary yet.
That bad yet? Okay, seems bad to me, but okay. But you're probably going to talk about something else, so
Yes, right. It does seem bad, but right. But yes, I am trying to get something else. So right, the effort of undoing that sloppiness doesn't seem quite worth it to me at this point. So yes, I'm being very bad and very sloppy. That's true.
Okay, as long as you admit it, it's always
That's
fun.
right. As long as I admit it, that's right. So yes. So now what am I trying to say? I'm trying to say that well, you know, so I'm trying to, in a very sloppy way, I'm trying to recapitulate the way I worked out these genus zero designs, genus zero Gaussian designs, well enough that I could get Mathematica to do calculations with them. But what
I'd like to, sorry, if you don't mind, I'd like to pause the recording for just a second.
Sure.
Okay.
Okay, so the basic point of my recapitulation that we just did, recapitulation of those calculations, is to point out a sort of stupid mistake, or maybe not so much a mistake as a failure of recognition. You know, there was something that I was doing and I just didn't quite recognize what I was doing. And so I really want to bring that out now, highlight how I was doing something without realizing it. So what am I trying to say? You know, I was trying to, the thing I was exploiting was the idea that a rational function of one variable can be thought of as, in a certain way, it can be thought of as a special kind of linear one parameter family of polynomials.
Mm-hmm.
And I mean, there's a little bit of fine print in there again, but we don't have to worry about it. This was the rough idea. This was the rough idea that I was exploiting in the calculation, that a rational function can be thought of as, in a certain way, as a linear one parameter family of polynomials, namely its k-rater polynomials. I just failed to recognize this as an example of a two-variable polynomial, which it obviously is. So, you know, it's a kind of two-variable polynomial. The two variables in question being, you know, k and x. And so yeah, I've been running through the alphabet so much, I'm, you know, sort of annoyed at, you know, I used f as a variable. I wanted to use f as a function name. Okay, I'll just use s as a name for my two variable polynomial. So it's like s of k and x. And Yeah, so it's right. Again, there's all these normalizations and things here, but roughly the idea is that you can encode a rational function as a two-variable polynomial in a certain way, and it's sort of first degree in this auxiliary variable k. Am I saying that right? Which one's the auxiliary variable? I'm not quite sure. But it's first degree in k, and it's some other degree in x. In our example, it's like sixth degree in x. We had all those sixth degree polynomials. So this is interesting because this is, I should have recognized this as this is the way that a lot of people think about algebraic curves. A lot of people think about algebraic curves as being given by a two-variable polynomial. Two-variable polynomial gives you a zero set. It gives you this equation, and this gives you an affine plane curve, and then you can complete it to a projective plane curve. And right, one of the things I want to emphasize here is that it's like, for example, if we look at the Wikipedia article on algebraic curve, in the first couple of paragraphs, which we will try looking at that in a moment, one of the things we should observe, if I'm not misreading too bad, is that the first couple of paragraphs is sort of devoted to explaining how the concept of algebraic curve is actually equivalent in a certain way to this concept of a two-variable polynomial. That a two-variable polynomial gives you an algebraic curve, and at first it might seem like this is a very restricted example of an algebraic curve, but it turns out it's actually not restricted. This is an unrestricted example. This is actually the universal example of an algebraic curve. So the point is,
despite the fact that it's linear in k or affine, first degree in k, is that the?
No. The point is that the first degree in k is what corresponds to the genus being zero. So this is giving us a hint how to get out of the trap of only being able to handle genus zero.
Okay, yeah. Yeah. So it is a restricted class of
this
one here, yeah. Yeah.
Well,
in that sense,
but maybe I failed to say it clearly. But I was trying to say that with just two variable polynomials in general, without the constraint on the.
Okay, well that doesn't feel restricted to me, but okay, fine, yeah.
Can you tell me why it doesn't feel restricted to you? Can I tell you why it does feel restricted to me?
Okay, sure.
Because this seems to me like the general example of an algebraic plane curve.
Yeah.
And I wasn't quite prepared for the idea that all algebraic curves are secretly algebraic plane curves. And in what sense is that true? It sort of depends, apparently. If you're doing birational geometry, then apparently it's a fact, and it's apparently a very basic fact that I somehow missed. It's like a crucial fact of the theory of algebraic curves, that every algebraic, exactly what are the fine print that we're talking about? Well, for example, every complex projective algebraic curve is birationally equivalent, allegedly, according to Wikipedia, for example, is birationally equivalent to a plane curve. And I'm still a little bit confused about how you can get away with that. Maybe it's true that it's maybe that word birational is doing a lot of work there. I'm still confused about how much work the word birational is doing there. Birational equivalence is a weaker form of equivalence.
Yeah.
than some stronger form of equivalence, but I'm not sure. Is it so much a weaker form of equivalence that it really allows this to happen, or is birational? How much of the work is birational really doing there? I'm not quite sure. So there's all sorts of things to try to understand here. But again, it's shocking, all the things that I discover that I didn't understand.
Yeah, I don't really understand that stuff terribly well. All I vaguely heard that, I mean, I've heard statements that say that like birational geometry is very, I don't know what to call it, very weak compared to
Coarse, very coarse.
Coarse is probably, compared to the
Yes.
the kind, and that it's like surprisingly uncoarse in very low dimensions or something like that.
And it may be only in the curve dimension. I think already by the time you get, by the time you get to surfaces,
that sounds familiar. I don't understand this stuff, but I've read.
Well, but let me emphasize a particular thing that still seems shocking to me. Let me try to state some propaganda to make it sound why it's part of why it still seems shocking to me. So this idea of, right, it's kind of like, I mean, we're very familiar, right? We're very familiar with the idea that planar sets, so to speak, are much more highly structured than sets. I'm talking about finite discrete point sets, and planar such sets seem much more highly structured than like ones that are embedded in three-dimensional space, for example, let alone infinite dimensional space. Right, because I mean, the claustrophobicness of two-dimensional physical space is responsible for why things get tangled up.
I mean, now it sounds like you're not, so you could, you could say like, no, they're not constrained at all. They're just, so I mean, isomorphism classes of them are just the same as in infinite dimensional space. But when you start looking at parameterized families of them, so like continuous families of them, then they become very noticeably different. So maybe, I don't understand this, but you could imagine that like plane curves are the same as arbitrary curves, but like families of plane curves are very different than families of general curves. That is, classifying them up to isomorphism might be the same, but not classifying some kind of moduli space.
Am I going in the right direction? I mean, my intuition was telling me that, that because the complex plane, which also known as the complex line, I hope it's clear which one we're talking about, the thing where the braids live, or the thing where the frame of a braid lives. That complex plane is so claustrophobic. I mean, what am I trying to say? I mean, I'm suddenly wondering whether, could it be true that maybe, I'm wondering whether the birationality somehow magically allows crossings to to reverse themselves or something like that. I don't know if that makes any sense, but right, but birationality sort of heals all singularities of curves. If they're, you can't notice punctures or singularities or anything like that. So I'm wondering if braid crossings might secretly be some kind of singularity that birational geometry can't see. That's just a stupid idea that I just thought of.
I don't know.
But I don't know. Did I make? I'm a little bit worried. Maybe I made my argument sound backwards or something like that. I was thinking, an algebraic curve branchedly fibered over the Riemann sphere. It's sort of like, a one parameter family of these discrete point sets. But it's not just these discrete point sets, it's these point sets that are trapped in a two-dimensional space. So that makes it seem like, that they would
They display some kind of grading phenomena as you move the parameter around. Which
but now you are getting confused with all these level slips between different homotopy groups and things like that. I don't know. Maybe I'll have to think about that part.
Anyway, all of this sounds like more sophisticated than we're.
Yes, right. We kind of jumped ahead a little bit, but right now we're trying to get right. So right. The actual plan, right. I mean, right. This started out for me as a way to try to generalize what I knew about genus zero designs to higher genus design. And that's a very interesting thing to try. But as you can see from the discussion that we just had, that it kind of jumped ahead for me, and it kind of emphasized again for me just how many things I am ignorant about algebraic curves in particular.
I remember looking at that
Yeah.
algebraic curve Wikipedia article.
Yeah.
I was trying to learn things about algebraic geometry and being sort of shocked that it starts out being all about plane curves.
Yeah, I mean, right. I mean, there are all sorts of more things to this. So, for example, what am I trying to say? That I mean, there's a whole bunch of things that I thought I knew that really did say that curves have that curves know something about higher dimensional spaces in which they're embedded. So, I mean, what am I trying to say? You can embed a curve in a higher dimensional projective space in such a way that it doesn't lie in any lower dimensional projective space. So, you know what I mean? It's really occupying a higher dimensional space, occupying it.
Like a twisted cubic or or the higher versions of the twisted cubic, whatever you call them. I think they as their name suggests, they sort of use all the dimensions they've got. Oh, so now you're trying to give an argument that.
Well, yeah, I don't know. I mean, how much does that rely on the embedding? How much is that? How intrinsic is that?
Yeah, right. Yeah. So
there's also things I'm confused about here. Or let me just mention a couple of other things. Just so you know how there's this basic Riemann-Roch combinatorics of curves, and how if you look at a genus zero curve, then the numerology goes one-dimensional space of sections over the trivial line bundle, 2 dimensions over the tautological line bundle, 3 dimensions. It just goes up like the integers. The dimension numerology of the space of sections of the.
Yep. The genus zero.
I think tautological is the right word for that line bundle over the projective line. Whereas if you take an elliptic curve and a nice ample line bundle over it, then you tend to get this other pattern: 1, 1, 2, 3, 4, 5, whatever. And if you figure out what's going on there, it's It's like there's a generator H in grade 1, but you need another generator X in grade 2. And then to get it all to work, I think you need another generator Y in grade 3. And, it's this kind of thing, Y squared equals X cubed. And then maybe H gets involved there or something like that. But, right, these numerological patterns via Riemann-Roch are giving you hints about the number of generators that you're going to need to generate this homogeneous coordinate algebra. And for certain special ones of these numerological patterns, it seems to be telling you that you need a lot of generators. So like, I guess at the other extreme is the hyperelliptic ones, which only need 2 generators or something like that. It's just like, right, it's like Y squared equals F of X or something like that. So all you need is X and Y as the generators or the variables. So, it's just like, it looks like a plane curve. But I thought that when you, right, as soon as you get beyond genus 2, hyperelliptic things stop being generic. And I thought that means that
yeah, you're giving a good
generators. What?
Yeah, you're giving a good argument here for why, in some sense, not all curves can be plane curves. You're basically almost, well, no, you still had Y squared. So I guess there's lots of more room for what can happen with Y. So never mind. I take it back.
Well, but I think for the most generic patterns, I think what happens is you will I think it looks like you're going to need a lot of generators. But I'm still confused with that, because that seems to be saying that that these things aren't plane curves in general. The most generic ones aren't plane curves, but maybe that's just maybe that's only when you're using some finer kind of equivalence than the birational equivalence. And in fact, maybe it even involves the
I want to say, does it involve a choice of ample line bundle?
Right, might involve, yeah, which is a choice of, I was going to say choice of projective embedding, but those are almost synonymous, a choice of ample line bundle and a choice of projective embedding.
I was trying to make it sound like it wasn't extrinsic, but then it like turns out that it is.
Yeah, right. I'm still confused about all of these things. So yeah, I mean, when we take a look at the Wikipedia article, it really looks like they're telling us birationally all algebraic curves are plane curves, basically. But I'm still resisting that conclusion in general. But maybe that's maybe birational. Maybe the word birational really is doing all that work, or maybe it's not. I don't know. I'm still confused about to what extent. To what extent is it true that all algebraic curves are plane curves? But like I say, this is so this is very good stuff for me to learn about. There's obviously all sorts of important things here that I never learned about. But again, this is all jumping ahead. We're still trying to get back to things we were trying to understand here. So let me see if I can sort of retreat back to where we were supposed to be. Well, first of all, let's try to say a little bit more about how the genus 0 case is getting incorporated into the picture here. So what am I trying to say? So, supposing you have like again, I'll for the moment I'll work over the base field of complex numbers here. So we have the complex numbers, And then we have this variable k. So this kind of, again, depending on, this could be giving us the affine line or the projective line, depending on whether we're doing birational geometry or ordinary algebraic geometry. But it's giving us some kind of line. You know, one variable is giving us a line here. And what am I trying to say? That, right, let me use the round brackets, you know, to indicate that we're doing birational geometry. We're working with fields here. So I've got K. And then I want to put in something like X. Sorry, I'm not quite sure how to notate this. Let me go back to the square brackets for a moment. I understand how to notate that a little bit better. I got K, and then I introduce a new variable X. But I'm gonna put in a relator which says that T of X equals 0. No, never mind that. T of X equals K. In other words, I'm going to put in a relator which eliminates the variable K, the original variable K. And you know, let's make T be a rational function here, right? Because you can do that, right? You can, if you have a rational function T, you can write out this, you know, you can say the numerator equals K times the denominator or something like that. And that's a way of
what's T, a rational function or a...
T is a rational function here. Yeah, again, I'm being a little bit sloppy here about the contrast between birational geometry and more than birational geometry. But roughly speaking, this kind of relator eliminates the original variable K and replaces it by a new variable X. So, right, you've started out with one genus 0 Riemann surface, and you've now covered it by another, you know, covered it with some multiplicity, by some degree, with another genus 0 Riemann surface. Riemann surface, a Riemann sphere. All right, a genus 0 Riemann surface is a Riemann sphere. So you've got one Riemann sphere covering another one, and so basically you've just eliminated the variable K in terms of the variable X. So this is the right. This is how genus 0 curves work. So right, and so what we're saying is that the fact that you can think of a rational function as a linear family of polynomials, that is right, that is showing us how genus 0 curves fit into the phenomenon of all curves being birationally being plane curves. You know, when you think of a genus 0 curve as being birationally a plane curve, you know, you're giving this 2-variable polynomial, and it's linear in K. So yeah, so these 2-variable polynomials that are linear in K, that's, you know, morally the same thing as these rational functions. And, you know, so those are things of, you know, just covering the Riemann sphere by a different Riemann sphere. So it's just the genus 0 thing. So, you know, that's what's happening in the theory of genus 0 designs. You're getting these designs where the canvas is itself just a plain Riemann sphere, but it's got, you know, many tiles on it. So it's got many lozenges on it. So it's covering the original Riemann sphere by by a high degree or something like that. So, all right. So, okay. So let's play around a little bit with the idea of trying to adapt our method of concretely calculating with genus zero designs. Let's now try to use these ideas to think about possibly trying to adapt those calculations to the case of higher genus. Okay, so what are we saying here? So now we're saying, let's see if I can figure out what we're saying here. It sounds like we're saying that, yeah, this doesn't go as smoothly. I'm not sure how well I understand it, but it's interesting. So what am I trying to say here? So we're now imagining that we have some higher dimensional design that we conceive of it combinatorially to begin with. So it's got some, I don't know what it looks like, but it's got, broken up into lozenges. It's got these little green vertexes. Sorry, that was supposed to be green. I'm pretending that I'm drawing an actual design here. It's got greens and it's got blues and it's got reds. And who knows what it actually looks like? Sorry, it was supposed to be red. And these edges are supposed to be connecting vertexes of different colors and stuff like that. So it starts its life just as a purely combinatorial object, but the concrete calculations that we're talking about seek to turn this into an actual algebraic curve. And in fact, an algebraic curve that's defined over, I was going to say over the rationals, but I guess the point is it's actually in general defined over the algebraic numbers, which is why it gets sort of acted on by the Galois, absolute Galois group. So how does this work? So don't tell me, let me think. So once again, we're going to have the three Young diagrams, right? We're going to have a Young diagram for the greens, a Young diagram for the blues, and a Young diagram for the reds. And it's going to have some, who knows what it's going to look like, but it's going to have different lengths, some sort of Young diagram. But now the Young diagrams, right? And we can do a combinatorial calculation of the genus. But now, the combinatorial calculation of the genus is going to be non-zero. So again, let's just remind ourselves of how you do the combinatorial calculation of the genus. So it's something like you take, the degree, the number of lozenges. That's like the degree. So I'll say degree, and that's sort of corresponding to the bulk of the Riemann surface. So that's that's where you ignore the branch point. So you've got this thrice punctured Riemann surface, and the thrice punctured Riemann surface, its Euler characteristic is basically -1, if I'm not screwing up. And so you've got d times -1, or negative d. But then you have, the number of rows of these Young diagrams. Those are the branch points. We're counting, right? So that if there's 3 rows in the green Young diagram, that's the 3 copies of the green branch point. And et cetera. So we're adding the green number, the number of, right, maybe I should write R for the rows or something like that. Number of rows of the green Young diagram plus the number of rows of the blue plus the number of rows of the, presumably this is some version of Riemann-Hurwitz or something like that. Riemann-Hurwitz formula for the Euler characteristic or something like that. Red or something like that. Okay. And this should be the Euler characteristic. And then you can convert the Euler characteristic to the genus or something like that by doing what? By dividing by 2 and subtracting 1 or something. I don't know. It's something like that. Taking the negative, I don't know. So, okay, but now how are we supposed to get a system of equations out of this? So, right, I guess the point is, right. So the vague idea now is that we're going to take, am I saying this right? That what should we take for the variables of our system of equations? We should take the variables to be the coefficients of a two-variable polynomial. So the two variable should be k and x again. And we should try to figure out, well, right, to get this to work, we should try to figure out what degree these polynomials, these two variable polynomials should be, what degree separately in k and separately in x. I think that's what you should do. And right, and the degree in x should still be, the number of lozenges. That's the number of times that it's wrapping around. That's the degree of that wrapping. So it's just, I'll just say number of lozenges or something like that. Because again, we're trying to think about this in terms of, starting with the combinatorial object, turning it into this system of equations, and the solution to the system of equations is supposed to be something like the actual analytic or meromorphic or holomorphic design or something like that, but with involving irrational numbers that get acted on by the absolute Galois group. As you say, how did you say it? There are new numbers, the new numbers that you need to create these new spaces.
Yeah.
So the degree, so it's still clear that the degree of this two variable polynomial in the x variable, that's still just perfectly sensible. It's, the number of roots that each thing should have. The size, the fiber size. But the question is, what degree should we have it be in x now? Okay. And previously in the genus 0 case, the answer was something like always 1, right? Yeah, basically the degree 1 is what corresponded to those rational functions. Those genus 0 things. But now the whole point is to try to get beyond that. So one of the big questions here is, what should we now take for the degree of these two variable polynomials in the variable k? Do you have any opinion about it, or should I just tell you my idea?
Well, the dumbest, obviousst idea is that it's just like if you're wanting so like for a genus 0 cover, you wanted polynomial that was degree 1 in k. And so for a genus 1 cover, you want it to be degree 2. Sort of like the equation for an elliptic curve has like.
I think you're on the right track. I'm not sure how on the right track you are. Yeah, go ahead.
Yeah, well, no, I probably already don't believe that quite anymore.
Right, but it's still on the right track. Right. Right. There's some very naive guess or something where we just say take the degree of this to correspond to the genus or something like that, or maybe slight offset or something like that. Yeah. But it's probably going to be.
Yeah.
It's probably going to be more complicated than that, but I still think it's sort of vaguely similar to that. I mean, right? I've been sort of
Do I get partial credit?
Yeah, I think so, because, right, I've been staring at, right, there's somewhere in Wikipedia, I think, there's some table, maybe it's even in this same article, maybe we should look in that same article on the algebraic curve or something. There's some two-dimensional table, I think, where we should really check that article now and see if they
Well, you're
have.
getting me curious. Tell me what this table does, and then I'll be dying.
Well, it has one axis. It's it's a discrete table. So one axis is the degrees in the first variable x. The other one is the degrees in the second variable y. And the number in the table at the corresponding grid point is the sort of expected
the generic
genus.
degree of the genus of the curve. Yeah.
Yeah, something like that. And then, so we should actually look for that like almost right now. But on the other hand, for the thing that we're trying to do, we're sort of trying to invert that table in one of the variables or something like that, right? We're starting out knowing the expected genus or something and knowing one of the degrees, and we're trying to figure out the other degree or something like that.
Right.
So it's something like that. But I think what I was actually going to say was I was going to say something like, let's say as low as you can get away with or something like that. As low degree as you can get away with. Or something like that. I mean, what am I trying to say? Or maybe what I mean is, maybe you should start out with a random choice for the degree and then see what the dimension of the solution space that you get is. And if it's too big, then just keep on trying to lower the degree until you hit a wall or something like that. And hopefully at some point you'll hit some point where the dimension of the solution space is 0. And when you hit that point, you're probably there. Now, right, it'd be good. I mean, what you were hinting at and what we should think about at some point is how to try to predict ahead of time what degree you should pick in order to get the dimension of the solution space to hit 0. Also, I don't remember to what extent I already emphasized this sufficiently, but when I talk about the dimension of the solution space hitting 0, I forget whether I said this or not. There's a certain amount of gauge freedom to be dealt with here. So, it's the dimension out of the solution space is only 0 after you account for, the triple transitivity gauge freedom in K and the triple transitivity gauge freedom in X. Although, when we're doing this higher genus case, we sort of have the variables K and X jointly working together. I mean, K is very special because the variable K is giving us the projection. But what am I trying to say? I mean, I have a feeling there might be some triangular matrix. Instead of just having a separate triple transitivity for each of the two variables X, K and X, there might be some mixed gauge group that it affects both K and X, so with the idea that, X is depending on K or something like that. I didn't really get very far with that, but I mean, just, if we try to figure this out, then, then there's, there's the idea that we want to, eventually, we want to eventually hit, right? In order to know that you have a correct answer, you should hit a 0-dimensional space of solutions.
Right.
And but in order to even define what 0-dimensional means, you have to take into account the gauge freedom in an appropriate way.
Yeah.
And I was just thinking out loud about what that gauge freedom is going to be like. So So this is kind of where I am. This is kind of where I am. So I didn't I didn't do any concrete calculations yet with the higher genus. I still have those concrete calculations that work pretty well with the genus 0. I didn't actually do any concrete calculations with the higher genus, but I'm trying to think out loud here and sketch out an approach to doing the higher genus case. And
of course, it'll be good to try to do the elliptic curve case that you just already have beaten to death.
Yeah, that's a good example. There are other
0 reduction, but that is the same setup that you love to study, the same example you love to study.
Yes, that's right. That's right. There are also some other good toy cases that are higher genus, but that are very simple for various reasons. There are other good toy examples to fool around with. Let's see. Is there any? Oh, okay. Maybe I'm sort of running out of things to say here. I'm trying to think out loud about, are there big things I've been forgetting to say so far? Or were you going to comment on anything here or ask anything?
I've been starting to peek at this Wikipedia article.
Let's do that. Can we have some fun? So
yeah. I'll share my screen and show this.
Okay.
I think
I have been sharing my screen, so you're just going to steal.
I think I can override you here.
Okay.
So,
okay.
I don't know if this.
My computer. I'll just read your screen here.
This is the first thing that looks like an actual table. I don't know if this is what you meant.
Well,
it looks weird.
I was hoping for a 2-dimensional.
Yeah, I know. I didn't see any really terribly exciting tables here. They're all sort of 1-dimensional.
And I'm trying to figure out where I might have. Oh, well, no, wait. What about this by degree thing here? Let's see.
That's a curve in. Maybe that is what you meant.
Yeah, I mean, it's almost like they're giving 2 rows from a table here. Isn't that what?
Yeah, they are. They're like leaving out.
But
giving the second and third row of a table.
So they are talking in the language of coherent sheaf cohomology, which in principle, maybe I'm supposed to understand that language and understand how it compares to the language that I've been using. It would be good for me to, learn more of that language. But I'm not sure I completely. Oh, that's right. I don't have any cursor control here.
So
I just have some vague memory of seeing some 2-dimensional table in Wikipedia somewhere. But yeah, but this is the kind of thing.
So here, I think this is like they're talking about like a polynomial in 2 variables that has degree specified for each variable. And here, one variable has degree 2, and the other variable has degree that keeps changing. So that reminds me a lot of like hyperelliptic curves, where you get like x squared is some polynomial of y.
Yes.
You're seeing something like as the degree of the polynomial in y goes up, then the genus, maybe this is like the generic genus, goes up in a sort of linear way. Which sounds, it sounds right, except it doesn't sound right, because like for x squared equals y cubed, you'd get an elliptic curve. No, so you'd get a curve of genus 1 when this was 2, 3, according to me, but they're getting 2, 2 gives you genus 1. So
all right, there's a number of things confusing me. So first of all, they're talking about curves in P1 cross P1. I thought I was expecting them to talk about curves in P2.
Well, maybe that's why I'm so confused. Let's see.
A different
game. Here it is in P2, but here they they don't talk about separate degrees for each variable. They just talk about degree
Well, that's interesting.
K.
Yeah.
So they're getting a one-dimensional table, which you should be able to, in theory, refine to some kind of two-dimensional table.
Yeah, I mean, again, I was, I was using a more naive thing just in terms of polynomials, whereas here they're talking about coherent sheaf cohomology.
Well,
Mm,
well, yeah, they're just figuring. I don't know. They're using some trick to figure out the genus of a curve, given its the degree
let me
of
see
the
what they're saying.
polynomial defining it.
Plane curves of degree K, which can be constructed as the vanishing locus of a generic section.
So the which can that's a removable clause, I believe. That is, it's a clause that you could cross out without making it false. And so they're saying it grows like a triangle number. So
Right. But then there is something about. Yeah, I mean, there's so much of this stuff that I need to understand. What am I trying to say? That this, right? I mean, there are very sophisticated definitions of what a hyperelliptic curve is, but there are also very unsophisticated definitions, aren't there, in terms of like a double cover or something like that?
yeah, I think that the main definition that Wikipedia gives is a fairly unfancy definition. Well, this is a little more fancy than I thought, but it's a little more general than I remember. But it is basically, I think it's saying what you said, that it's, I think they say that somewhere else that
it's manifestly a plane curve as opposed to,
in this definition it is, because they're giving like a formula for it. But then I think there's like a more intrinsic definition that says that it's,
well, let's see what they say about the genus of the curve. Let's see what they say about the genus of the curve.
Okay.
Degree of the polynomial in terms of the genus of the curve.
Yeah, so you get this thing that two different degrees give you the same genus. Like degrees 3 and 4 give you an elliptic curve.
Right. So okay. So, I mean, this sort of seems to be saying that I'm not sure if I'm overinterpreting, but in a very simple-minded way, they sort of seem to be saying that the genus grows at half speed.
Yeah.
And I, so I was just stupidly trying to generalize that, if the genus grows at half speed for a double cover, then why not grow at 1/3 speed for a triple cover?
Now I can't remember what those kind of, there's some name for things like that, like triple covers or n-tuple covers. Do you remember a name for that? There's some buzzword for where you keep playing this game past the hyperelliptic case. Oh, trigonal curves there is the case that you're the gonality is the general concept. I just was hoping we could.
I mean, again, there's so many things I didn't think through here, but I thought in this theory of designs, it seemed to me that we really should consider the degree of the two curves separately. But I did idly think about, some sort of joint degree or something like that.
Sorry, the degree of which two curves separately?
did I say that I didn't mean to say degree. I didn't mean to say curve. I meant to say that the degree of the curve, the degree of the polynomial of the two variable polynomial with respect to the two variables.
Yeah, that makes.
I thought that, you know, certainly one of those degrees makes a lot of sense in the theory of design.
Yeah.
But I thought maybe the other one is worth looking at too, but maybe it should be something slightly different than the degree with respect to the other variable.
Yeah, so I think this concept of gonality, which is a terrible name, is what you're after for like so like they say genus 0 curves have gonality 1, hyperelliptic curves have gonality 2. It is this, they're making it sound very algebraic here, but I think it is this business of like curves that can be described by an n-tuple branched cover of the Riemann sphere have gonality n.
Yeah, so there is we can make up a conjecture here, right? We can say that maybe the gonality is precisely the degree that you should use, or almost precisely the degree that you should use, and maybe that will always give you this degree 0 degree 0, maybe that will always give you this 0-dimensional space of solutions. But that's just a stupid wild guess conjecture. But I mean, in terms of this article, I'm not so much focusing on trying to figure out the design stuff. It just seems like there's a lot of stuff in this article that, again, it's shocking how much stuff in this article is. Seems like very basic stuff that I didn't know. So I'm very tempted to try to learn from. Again, I'm just annoyed by the fact that, you know, you have control of the cursor. I can't move it. So I'm just going to get my own copy of the article here. Go ahead.
No, go ahead. I want to quit fairly soon.
Sure. We're just about done, but I
can stop sharing if you want to.
No, I'm just trying to get to the article here though. So where is it? Algebraic curve?
That's where I first went, and then I went to gonality of an algebraic curve.
Right. So right, I gave my usual disclaimer as usual, right? That I always had the feeling that there's all sorts of really important stuff that I forgot to say, including the disclaimer. Let's see. Okay, so plane geometry, plane projective curves. Well, all right, yeah. So there's just a lot of stuff for me to go home and think about. But in particular, there's like let me just close by saying that there's so many other topics that we want to get back to. So I mean, you know, very recently we started thinking about some basic number theory and some ways of thinking about that. I'm hoping to get back to that very soon. What were you saying?
Yeah, I have this feeling that you were leading up to something with your tale of the 20th cyclotomic field and some kind of conjecture about how you can get all fields between a field and its Hilbert class field in some kind of concrete way by using representatives of the ideal classes. And I have a feeling that, well, this false conjecture of yours, I have a feeling that I was struggling to keep up with you, and I didn't really get the point enough. And then afterwards, you sent me an email where you sort of summarized some of the reasons for how this was supposed to work. Anyway, it feels to me like there'd be like some really fun stuff to do there that we didn't quite get, at least just to see like, well,
Right. I mean,
like how you hit this brick wall or whatever it was, but I didn't. So.
Right. I mean, the point of a false conjecture is really lost if you can't even feel why it should, why you might want it to be true.
Well, or then even if you want it to be true, why it's false. Yeah. So I didn't see that either.
Right. Well, so, but
I sort of think I sort of vaguely, it's cool, and it sort of reminds me in some weird way of the Jugendtraum, because it's sort of like you're trying to get some kind of quote concrete way of describing a field extension.
yes,
Stuff.
yes. I mean, all of these things are. Yeah, I mean, like all of these. Yeah, there's some very basic ideas, very interrelated. The art and reciprocity theorem and the Jugendtraum and other stuff. So yeah, I'm hoping to get back to that pretty soon. But it's a lot of that is entangled with the stuff that I am talking about here, about designs and stuff like that. So we'll see how it goes. We'll see how it goes. But okay, so thanks a lot. And I'll see you next week, presumably.
Yep.
Okay.
Okay. See ya. Yeah.
Bye.